Aye, this will be Group 10's analysis of a site that will eventually become a blood transfusion centre. In this analysis, things that we'll look at will be the local climate and natural resources, the potential energy demand of the building, as well as renewable resources that can be built on the site, such things as hydro, wind and solar. The overall aim of this analysis is to lower the potential energy demand, lower the carbon footprint of the building, as well as incorporating renewable resources into the building.
Okay, so we will analyse the local climate and natural resources section of the project. It's important first of all to put the site into context. The site is located in the western periphery of Edinburgh. It is around 7 kilometres from Edinburgh Airport and 11 kilometres from Edinburgh city centre. It's also well connected to the rest of the city through main routes such as the A71 and City Bypass. There is also good access to other areas of Scotland through motorways such as the M8 and M9. So site orientation. In the context of Heriot Watt, the site is located in the northwest boundary of the research park. There is also access to this through the road that flows through the research park and subsequently through the Heriot Watt campus. The open and green space of the site provides potential for the use of wind turbines and solar PV technology, with the open space ensuring that natural resources such as wind and sunlight can be harnessed consistently.
Here is the SunPass diagram for summer 2017. It shows the amount of sunshine the building can possibly get during the day. It also shows the shading created by the sunlight around the building. Both south and east facade are exposed to more sunlight than west and north facade. Here is the SunPass diagram for winter 2017. The sun position is a lot lower than summertime. Therefore, the amount of sunshine during the day is less than summer. The south facade potentially gets more sunlight than other three directions. The building orientation should be well designed in order to harness enough sunlight and avoid unnecessary shadings. Some basic climate information of Edinburgh Airport area is provided by the Nicograph, include daily sun hours, mean of maximum and minimum temperature, average temperature, comfort temperature, and relative humidity. Daily sun hours are quite low apart from May. It is reasonable to suggest the lighting source should be mainly rely on artificial lightings, and the orientation of the building should be designed properly in order to maximize the solar gain. The blue line shows the comfort temperature and the yellow line shows the average outdoor temperature. The comfort temperature of each month are all higher than the average temperature. This means in general, heating is required across the whole year. Relative humidity in this area is at a medium level, which is an acceptable level.
So site topography is also an important feature of the site. The map on screen shows site elevation is slightly higher towards the west of the site and flattens towards the eastern end of the site. There are also no major changes in the relief of the land from north to south, showing that the land is relatively flat. As shown by Edinburgh Council's topography map, the site has an approximate site elevation of 269 feet, which equates to around 82 metres. Overall, the topography of the site shows that there are many sustainable and renewable opportunities.
Due to the topography, some sustainable drainage systems can be applied to surface water management. Here are the 6 options of the sustainable drainage systems that are suitable for the site. Green roof, rainwater harvesting, and permeable surface for car park can be designed as parts of the building services. Swales, channels, and rain gardens are the surface water management options suitable for the building and the site as a whole.
Okay, so the map on screen shows the nearby hydro sources, thus implying there is a certain degree of potential for hydro energy generation. Nearby sources include Heriot Watt Pond and the Union Canal. Whilst there may be potential for this form of renewable energy generation, it remains to be seen within the rest of this video whether this resource will be utilised within the project.
When considering energy generation using the sun, there are various types of solar panels which can be used on a respective building. First, there are solar thermal panels which use the heat of sunlight to generate electrical energy. Additionally to solar thermal panels, there are solar photovoltaic or PV panels. They absorb sunlight and transform it into electricity by utilizing a silicon-based technology. The different types of solar PV panels are thin film panels, which are the least efficient and therefore use much more roof space, however perform better in low light conditions or in extreme heat. Then there are polycrystalline and monocrystalline panels, which both are more expensive. The main difference between all three of those panels starts during the process of creation. For the site, we are certainly going to use PV technology, with a tendency to monocrystalline panels, due to their efficiency and longer lifespan of up to 30 years. Thermal panels, on the other hand, have a much shorter lifespan and are less effective in winter months, with Edinburgh only receiving the average of 1,384 hours of sunlight per year out of a possible 4,383. This would not be the right choice. To maximize the sunlight received by any photovoltaic technology and how effective it will be, the surrounding area and possible shade needs to be taken into consideration. To receive the most solar energy, all panels should face south. Additionally, the angle at which the solar panels are set can have an impact on how efficient they are.
In this section, we're going to be talking about the hydro and the wind power that we're going to be using for electricity generation on site. When looking into hydropower, we had been informed by Jamie that we had hydro sources available, but they were all low-flow waterways, with the Union Canal as our most likely option. We therefore looked into Pelton wheels and other low-flow hydropower technologies, but could not find any technologies that were efficient enough with the depth and the flow that was present in the Union Canal. We figured that by using a Pelton wheel in the Union Canal, it could only generate about 0.4% of the annual energy demand per unit, and it was determined that it would simply not be efficient enough. Hence, we scrapped the idea of using hydropower as a renewable resource for our site. As hydropower would not suffice, we looked into wind energy to see if this was a better fit for our site. Scotland is already a windy and partially flat country, both of which are perfect conditions for wind turbines. As mentioned previously in the video, the site is a perfect example of this, as it's a very flat site with open land areas on all sides. We therefore decided that wind power would be a good option for one of the two on-site renewable electric energy generation methods. As the graph on the screen shows, the wind is mainly coming from the southwest and has an average wind speed of about 5.0 meters per second. We started by looking into rooftop wind turbines, but quickly found out that they would not suffice, as their annual energy yield was way too low for our site. We therefore started looking into some pole-mounted wind turbines, and we are aware that there are some regulations related to putting up the pole-mounted wind turbines. But for this purpose and for this exercise, we have decided not to go into too much detail about this. The wind turbine we thought would best fit our site was an Endurance E312, which is 36 meters tall. At this elevation, it was estimated by us that the wind speeds would be about 7 to 8 meters per second due to wind speeds increasing proportionally with elevation as a result of less surface friction and less turbulence the higher up from the ground you get. The big problem with wind turbines are the capacity factors, and it describes what power the wind turbine actually puts out compared to its absolute max output. With the max output being the power it would yield if it was running on wind all the time throughout the year. As it doesn't produce power all the time, the value is usually only about 30%, but some wind turbines can have a capacity factor of close to 40%. Hence for our site we set to an average of 35%. As there are a couple of trees surrounding the area, together with some buildings that would block out some of the winds. We also looked at options to install a bigger 250 kilowatt wind turbine, which would have produced 40% of the needed electricity demand annually, but we decided it was too big for the site and scrapped the idea. With some approximate calculation and qualified guesses, it was estimated that one of the turbines could produce about 200,000 kilowatt hours per annually, or about 10% of the electricity needed for the building. This is why we decided to go with 2 of these turbines and cover 20% of the total needed electricity for the building just from wind power.
When analysing the likely energy requirements of our subject building, the following was found. Month to month, as you would expect, the winter months see an increased demand for natural gas, with this demand peaking in January. The summer months see a dramatic drop in the demand for natural gas. Electricity demand remains somewhat constant throughout the year. We would like to look at ways in which the building's demand for natural gas is not as high in winter, and at how electricity demand can be reduced throughout the year. When looking at a breakdown of how this energy is being used in the building, the blue bars show that heating, ventilation and air conditioning is the biggest contributor to energy demand, particularly in the winter months. It was also noted how the electricity demand for lighting is constant throughout the year, despite the increased amount of daylight hours in the summer. We then looked at energy demand on a day-to-day basis and calculated the load factor for the demand profiles of these days. For energy suppliers, a demand profile with a higher load factor or a flatter profile is easier to meet. These energy suppliers ideally want to avoid peaks and troughs in demand profiles to allow for a smoother, more constant delivery of energy. A steep gradient in demand may require a number of power stations in standby to be ready to meet that peak. On November 1st, at the beginning of winter, we can see peaks in gas use in the morning, afternoon and evening. This gives it a load factor of 48%. Electricity use is quite constant from around 4:30 am until around 9 pm, giving a load factor of 69%. As mentioned, we would like to give the building a smoother demand profile with a more constant delivery of energy, which will not only reduce the overall energy demand, but make it easier for suppliers. Then looking at January 1st, right in the middle of winter, it shows similar characteristics to November, with a slightly more constant use of gas, giving a load factor of 55% and almost no change in electricity demand. Skip forward then to June 1st, in the middle of summer, and as expected we see very little gas use and a load factor of 45%. Electricity use again remains quite constant. And then looking at August 1st, we see quite sporadic use of natural gas, creating extreme peaks and troughs and a load factor of 40%.
With the previous slides looking at the potential energy demand of the building, here are technologies available to help further reduce the demand. Smart meters are a way of giving an accurate reading in the transmission of electricity, gas, water and heat consumption measurements. The reason you'd use smart meters is it offers a real-time data, a display of your energy consumption, multi-tariff function can be added, as well as automatically controlling your electrical appliances, as well as reducing the cost by increasing energy consumption during off-peak cheaper tariff periods. The problem with smart meters, in conjunction with the renewables that would be on site, as installation can be a problem from companies when there is renewables. It only shows what you're buying from suppliers, not what you're generating, so 2 meters are needed to help them coexist with each other. On LED lighting, the reason you use LED lighting is it's more energy efficient than other lights, extending life, a cold temperature operation which is better for the blood transfusion centre, a durability and low maintenance, install eco-friendly, the controllability, and it offers no IR or UV emissions. It's similar to solar panels, it's a perfect combination with solar panels, and uses a direct current which also helps the renewables as you're wasting less of that energy produced. On with the glazing, it is an improved thermal performance. You can have double or triple glazing, reflective coatings, reduces the cooling, which in terms of the renewables is saving energy as you're having to waste energy by heating the building, as well with the mechanical heat recovery ventilation. The mechanical heat recovery is just a system that offers, by bringing fresh air into all habitable areas without letting the heat escape. The benefits, obviously, I've mentioned fresh air, warm and well ventilated areas, reduces the heating bills, which again is saving the energy that is produced from the renewables and helps retain over 90% of the heat. Other types of technologies available to help reduce the energy wasted from the renewables is insulation, as well with the SIPS panels. SIPS panels are insulating foam cone stands between two structural facing, typically OBS boards. The advantages of this is it's comfortable for the occupancy, it maximises space, so there's more space in the building to be used for whatever the purpose. The speed of the build, it's more energy efficiency, and it has more soundproofing qualities. With this, where it works with renewables is, again with the glazing or the mechanical heat recovery ventilation system, is that it's just saving energy that could be wasted on trying to heat the building.
We started this video by telling you how we were going to make the blood transfusion centre have a lower potential energy demand and a lower carbon footprint by smartly incorporating renewable resources. The resources we chose to use were solar PV panels and wind power for electricity, and solar thermal panels, as well as a biomass furnace for heating and to replace gas heating of water and spaces. The energy sources are all renewable and will therefore, just by using them, make the building have less of a carbon footprint by reducing the carbon emissions both directly and indirectly coming from the building. It is not as straightforward when it comes to flattening energy demand profiles, as the resources will all impact the profiles, meaning that they have to be incorporated smartly into the building, and by storing the energy throughout the night and using it through the day when the peak demands are occurring, one can successfully flatten out the demand profile. The storing does not affect solar power as much, as its highest energy yield is during the working hours anyway, but the wind can definitely be blowing throughout the night and hence be reasonable to store for the day. When it comes to biomass heating, this can be done whenever the building needs it, and the only storing the furnace needs is a storage for the wooden pellets or similar fuel that it's using to heat the building.